Alright, Lesson 1, Supplementary Readings. So according to the course schedule, we're going to be reading the Dragon book, starting at chapter 1, going to chapter 1.4. So, here we go. Programming languages are notorious for describing computations to people and to machines. Well, we know it depends on programming languages. Yada yada yada. Before a program can be run, it first must be translated. Yes, we already learned this. How to design instrument compilers. We shall discover that a few basic ideas used to construct translators for a wide variety of languages and machines. Okay, introduction. 1.1 Language Processors. Simply stated, a compiler is a program that can read a program in one language, the source language, translate it into the equivalent program in another language, the target language. We saw this already. So you have the source program, goes into the compiler, comes out as the target program. Simple. If the target program is an executable machine language program, it can then be called by the user to process inputs and produce outputs. So you put some inputs into the target program and it gives you some outputs. An interpreter is another common kind of language processor. Instead of producing a target program as a translation, an interpreter appears to directly execute the operations specified in the source program on inputs supplied by the user. So an interpreter, okay, that's interesting. So an interpreter doesn't create a target program specifically. It just reads in the source. Well, actually, hang on, wait a minute. Source program. Instead of producing a target program as a translation, appears to directly execute the operations specified in the source program. Right, so like this, for example, with the JVM, the source program I'm guessing would be bytecode, which is like an intermediate, essentially an intermediate representation of the program. So if this was Java, we would have a bytecode program feed into the Java interpreter, and you'd also give it inputs, and it just gives you an output. So you don't actually create, a target program with an interpreter. That's probably something that I want to remember, but I feel like that's something super basic. So I'm going to end up remembering that by the end of this course for sure. So I'm not going to add that to Anki. The machine language target program produced by a compiler is usually much faster than an interpreter at mapping inputs to outputs. An interpreter, however, can usually give better error diagnostics than a compiler. Okay. Because it executes the source program statement by statement. Right, okay. So the benefits of an interpreter are, better error diagnostics. That's interesting. Example 1.1. Java. Yeah, here we go. Java language processors combine compilation and interpretation. As shown in figure 1.4. A Java source code program must be compiled into an intermediate form called bytecodes. The bytecodes are then interpreted by a virtual machine. A benefit of this arrangement is that bytecodes compiled on one machine can be interpreted on another machine, perhaps across a network. Bytecodes compiled on one machine can be interpreted on another machine, perhaps across a network. But isn't that what a compiled program does too? Can a compiled program not be interpreted? Oh, right, because a compiled program is compiled for a specific architecture. So if you try to, you try to send it somewhere else, run it, it's not, there might be issues. Whereas with here, we're sending like an intermediate representation, a architecture independent representation across the network, for example, and it's being read by an interpreter on another machine. Cool. Okay. In order to achieve faster processing of inputs to outputs, some Java compilers called just-in-time compilers Translate the bytecodes into machine language immediately before they run the intermediate program to process the input. Okay, cool. So we send the source program to a translator, we get bytecodes or an intermediate program, then we send that to the virtual machine or the interpreter, which takes input as well and gives us our final output. It's a hybrid compiler. Okay, that makes sense. In addition to a compiler, several other programs may be required to create an executable target program, as shown in Figure 1.5. A source program may be divided into modules stored in separate files. The task of collecting the source program is sometimes entrusted to a separate program called a preprocessor. Yeah, if you've worked with C or C++, that's you'll understand this. The preprocessor may also expand shorthands. Yep. So in C++, you can literally write macros, and it substitutes it's essentially a substitution for a piece of code. You plug in the macros in somewhere in your code, and the preprocessor will go through and find wherever the macro is in the source code, and it replace it with the code that you want. Cool. The modified source program is then fed into a compiler. The compiler may produce an assembly language program as its output, because assembly language is easy to produce as output and is easier to debug. The assembly language is then processed by a program called an assembler that produces relocatable machine code as its output. I'm not sure what relocatable machine code is. Large programs are often compiled in pieces, so the relocatable machine code may have to be linked together with other relocatable object files and library files into the code that actually runs on the machine. The linker resolves external memory addresses, where the code in one file may refer to a location in another file. The loader then puts together all the executable object files into memory for execution. So, what is relocatable machine code? That needs defining. Software whose execution address can be changed. Okay. Might run an address 0 in one instance and an address. Okay, all right. Fair enough. So that's some pretty low level stuff, I guess. Partially built programs are composed of object modules, unfortunately called relocatables. Right. Okay. So it's just where were we? The book. So it's basically just it's just machine code. Relocatable machine code. Cool. Alright, so exercise. What is the difference between a compiler and an interpreter? So a compiler creates a target program, which is like basically an executable, whereas an interpreter takes a intermediate representation of the source code, and it also takes inputs, and then it runs like a just-in-time compiling sort of thing and gives outputs. So it's not actually creating a target program at all. It's basically just running it just in time, like running it and compiling it just in time. Cool. Again, I feel like that's not worth adding to Anki, because by the end of this course, we're going to remember this for life. What are the advantages of a compiler over an interpreter and an interpreter over a compiler? So, well, firstly, a compiler over an interpreter has the benefit of faster speed. It has like it can have orders of magnitude faster speed, because it generates an architecture dependent program is what I'm trying to say. Whereas an interpreter has an advantage over a compiler, because it has much better error diagnostics, because it's literally running the intermediate source code, intermediate representation source code line by line, so it can spit out errors with great precision, I'm guessing, because you have all the line numbers right there in the source code. Whereas if you're running some binary, you're not going to have that. What advantages are there to a language processing system in which the compiler produces assembly language rather than machine language? A language processing system in which the compiler produces assembly language rather than machine language. My guess is portability. So if your output is assembly language, you can. What advantages? Language produces assembly language rather than machine language. Yeah, it has to be portability, right? Because assembly language can be read on multiple different architectures, I'm assuming, and whereas machine language can only be read on basically the architecture that was built on. So I have to double check that. Machine language over. The source language translate. Is that what it was talking about? Relocatable machine code? Large programs often compiled in pieces. Okay. Oh, here we go. Okay, right. Assembly language is easier to produce as output and easier to debug. Assembly language is then processed by a program called an assembler. Produces relocatable machine code. Okay, so it's not really portability is the reason for that. It's easier to easier to produce as output, easier to debug. I'm gonna. Is that worth putting in Anki? Probably not. Screw it. We'll put it in Anki. Oh my god, I can't type. Benefit is assembly is easier to create, not easier to output, and is easier to debug. And that makes total sense. It's way easier to debug, source code than it is a binary. Okay. A compiler that translates a high-level language into another high-level language is called a source-to-source translator. What advantages are there to using C as a target language for a compiler? Well, I'm just going to guess portability, because C can run on multiple bunch of different things. Speed, because C can compile down to super efficient super efficient assembly, and obviously debugging as well. Easier to debug C than it is to debug assembly even. Yeah, that's my guess. But not sure if there is an answer for this in the book. Let's. Well, I mean, all of this, the preprocessor, assembler, the linker, the loader, that all translates to C perfectly. C has all of, like, C compilers have all those things. So, I guess using it, I actually don't know. Those are my guesses. I'm going to Google that. I don't know the answer. Those are my three guesses: portability, speed, and debugging. The various advantages using C as a compiler language, such as C as no. C as a target. Wow, looks like someone Googled the same thing we did. Using C as portability, existing compiler infrastructure. That's a good one. This is 100% ChatGPT generated, but it looks pretty accurate. Performance, debugging. Yeah, cross-platform development, yep. Which is related to portability, yep. Low-level features. C provides access to low-level features of the target platform, allowing for fine-grained control over memory and hardware. This can be important for systems programming, embedded systems, and performance-critical applications. Okay. All right, cool. Final question. Describe some of the tasks that an assembler needs to perform. Okay. An assembler needs to obviously output assembly code. Memory is terrible. Need to output assembly code and I want to say translate to the architecture. Like the assembler may have to be architecture dependent, but I'm not 100% sure on that. So let's go look at the actual answer. The assembly language is then processed by a program called an assembler that produces relocatable machine code as output. Large programs are often compiled in pieces, so really together with other object files. So the linker links them together, like different relocatable program. Yeah, I'm not really sure. This it seems like the book just says literally output. Oh right, no, okay, I'm totally wrong. So the assembly language is in process. So the assembler takes assembly language and produces machine code. I was completely wrong on that. So I'm going to add that to Anki because I'll definitely want to solidify that. Compilers. Basically, what does an assembler do? Yeah. This makes sense. Yep. Takes assembly language and, well, it compiles it. Well, let's just say converts because we don't want to confuse the words. and converts it into relocatable machine code. Cool. So source program goes into the preprocessor, modifies the source program, so it inserts, like it expands the macros. It does things like bring in source files. In the case of C++, it brings in like the header files into the output of the preprocessor. It does conditional compilation as well. I know you can basically use preprocessor directives, which is like a predicate or a decision, control flow to decide what code gets compiled and what code gets ignored, which is pretty cool. Then you chuck it into the compiler, gives you assembly, goes into the assembly, gives you machine code. Then a linker loader finally links all the library files and things like that. Gives you your actual executable. Cool. This is literally like describing C and C++ compilers, like G++ is pretty much exactly this. And actually, I am able to demonstrate. I'm going to demonstrate this because this is pretty cool. So this here, we can actually visualize this. So here I have this basic C++ program. Hello world. Let's put a macro in here. Let's I don't know, call it goodbye. Can you do strings as macros? We're about to find out. I have no idea if this is going to work, so let's give it a shot. So just define a macro wherever. When the preprocessor gets this file, it's going to go through. It's going to firstly bring in the IOStream library. Well, actually, no. I think the linker does that. Maybe it does bring in the entire IOStream library into the source code. We're about to find out. So then it'll look at this macro and say, okay, I'm going to go through, and anytime I see this in the source code, this goodbye identifier, I'm going to literally substitute this code in for wherever it is. So I'm hoping this will work. I have no idea if it's going to work. G++ will give us an error if it doesn't. So let's give it a shot. But I'm going to demonstrate what the preprocessor is actually doing, because this is pretty cool. So do I even have is G++ installed by default? Oh, we're about to find out. G++, hello world, dash E, which tells the compiler to stop after the preprocessor is done. And we're going to output that as hello world.ii. Hope that works. Seems okay. Now we can open that file, see what happened. Okay, so let's give us some space. So this is what happens after the preprocessor. This is what the preprocessor has outputted. So it looks like it's bringing in this IOStream library. I'm not sure if it brings in the whole library or not. Let's see if we can find any. Can we see our macro yet? let's just see how many. How do you go down? How many? Oh, well, okay. So it's 32,000 lines. So I would say that it's brought in the entire IOStream library. So let's go back to the top. Yeah, I would say it's brought in the, yeah. So I'm going to look for our macro. Okay, so I couldn't find the macro. Let's see if we can just look for. Wow, so it actually worked. That's cool. So, yeah, you can see there what it did. The preprocessor subbed in the macro. And it looks like it gets rid of all mentions of the macro because I can't find it in this file. Yeah, that's pretty cool. What else in here is interesting? I think, yeah, it looks like everything else in this file, apart from my little program down the bottom, is just the IOStream library. Cool. So the next step is actually compiling it, and that'll give us assembly language. So let's do that and see what that outputs. So just got to remember the command for this. It was G++. Helloworld.cpp. I believe it's dash capital S dot S for assembly will be the output. Looks like it worked, so let's check out that what should be assembly language. Cool. Perfect. Yeah, I'm not an assembly language buff, but here's our macro. Looks like it's doing stuff with registers. Is there any? Yeah, it's just like it's calling functions from the IOStream library. Yeah. So anyway, that's actually I wonder if there's like a main. Is there a main function? Main. How do you go next in this? Yeah, no, this is it. I'm guessing this is it. This is our main function here. So yeah, I really don't know what I'm looking at. I'm trying to look for our macro somewhere in the main function, but obviously it's been substituted for some value at some point. So it looks like it just gets called as maybe it's put in a register or something. Anyway, so that's the assembler. Sorry, that's the compiler itself, the G++. The next is the assembler. So let me remember how to do that. G++. I'm going to tell it to stop. All right, yeah, it's just the C. That's simple. It's just the C dash C. We're just telling it to compile into assembly language. Into machine code, and that's it. So yeah, just dash C. That gives us an object, relocatable machine code object. So if we try to view that, I'm pretty sure it's all messed up. Yeah, so we can't look at that, but we can we can use the object dump. This is annoying. Object dump tool. And we have to disassemble and demangle that. Hello world.o. So hopefully we can see what's going on here. So, okay. So we can see what was going on in this was actually shown to us in the first lesson. So this is the result of the assembler. Again, we've got like registers over here, you've got assembly on the right, and then the substituted machine code on the left. Not sure there's anything in here that I can understand, but yeah, pretty cool. And finally, after all that, we can just properly compile everything, link it. The final step is the linker and the loader. That'll give us a.out, and then we can run that finally. Hello world, goodbye. Cool. Continuing on. Up to this point, we've treated a compiler as a single box that maps the source program into a semantically equivalent target program. If we open up this box a little, we see that there are two parts to this mapping: analysis and synthesis. The analysis part breaks up the source program into constituent pieces and imposes a grammatical structure on them. It then uses this structure to create an intermediate representation of the source program. We already saw that. If the analysis part detects that the source program is either syntactically ill-formed or semantically unsound, then it must provide informative messages so the user can take corrective action. The analysis part also collects information about the source program and stores it in a data structure called the symbol table. Alright, so this is new, which is passed along with the intermediate representation to the synthesis part. So, symbol table, it stores information about the source program. Okay, moving on. The synthesis part constructs the desired target program from the intermediate representation and the information in the symbol table. Okay. The analysis part is often called the front end of the compiler. The synthesis part is the back end. Constructs the desired target program from the intermediate representation and the information in the symbol table. Cool. Alright. Right, so it's just explaining the front end and the back end. If we examine the compilation process in more detail, we see that it operates in a sequence of phases, each of which transforms one representation of the source program to another. A typical decomposition of a compiler into phases is shown in Figure 1.6. In practice, several phases may be grouped together, and the intermediate representations between the group phases need not be constructed explicitly. The symbol table, which stores information about the entire source program, is used by all phases of the compilers. Okay, so read in the source file, we'll exit, we get a stream of tokens, then we get the abstract syntax tree, and then we get a more detailed syntax tree from the semantic analyzer after it does its type checking and its semantics correctness checking. Then we do the intermediate code generator, which can give us like a control flow diagram or some other intermediate representation. Machine independent code optimizer optimizes the code using assembly language, I guess. Code generator generates target machine code, machine dependent code optimizer. Yeah, okay, cool. So there's machine dependent code optimizer. Yeah, I assumed there was. Awesome. And I guess all of that at some point references the symbol table. Some compilers have a machine independent optimization phase between the front end and the back end. Machine independent code optimizer. The purpose of this optimization phase is to perform transformations on the intermediate representation so that the backend can produce a better target program than it would have otherwise produced from an unoptimized intermediate representation. Since optimization is optional, one or the other of the two optimization phases shown in figure 1.6 may be missing. Cool, good to know. Lexical analysis. The first phase of a compiler is called lexical analysis or scanning. Lexical analyzer reads a stream of characters. We already know this into meaningful sequences called lexemes. So for each lexeme, the lexical analyzer produces as output a token of the form, token name, attribute value. That passes on to the subsequent phase, syntax analysis. Okay, so a lexeme, from what I can tell, a lexeme is essentially like the individual word. So let's have a look here. So that would be a lexeme position. This would be a lexeme, the assignment operator. Then this would be a lexeme. This would be a lexeme. This would be, but it looks like a token from what this book is saying is basically like for each one of these lexemes, you have the token name and the attribute value. So the attribute value in this case, like the token name. So for this lexeme here, initial, the token name would be initial, and the value would be, I don't get it. What would the value be? It wouldn't be like the variable value. Ugh, I'm confused. Let's keep going. In the token, the first component, token name, is an abstract symbol that is used during syntax analysis. In the second component, attribute value points to an entry in the symbol table. Oh, okay. All right. I just needed to read ahead. Information from the symbol table entry is needed for semantic analysis and code generation. For example, suppose a source program contains the assignment statement. Yep. The characters in this assignment will be grouped into the following lexemes and mapped into the following tokens. Yeah, so a lexeme is just like each individual word, basically like a meaningful word, but then the token can have like additional info. So position of lexeme that would be mapped into a token ID 1, where ID is an abstract symbol standing for identifier, and 1 points to the symbol table entry for position. Okay, now it's starting to make sense. The symbol table entry for an identifier holds information about the identifier, such as its name and type. Now it's all coming together. So we have like what was the JS Paint? So we have something like this. Symbol table, and it has like ID, a column for IDs, and then like the numbers. And then you could also have like value. Actually, no, this doesn't make sense. It would be like this. It'd be like this. And inside the column, you would have like extra stuff, like the name, etc. So we'd be referencing from a token. We would have our token ID 1, which would point us to our exact reference in the table. Cool. The assignment symbol equals is a lexeme that is mapped to the token just equals. Since this token needs no attribute value, we have omitted the second component. We could have used any abstract symbol such as a sign for the token name, but for notational convenience, we've chosen to use the lexeme itself as the name of the abstract symbol. Okay, so how would that work in our example? I guess you would just have well, I guess it doesn't look exactly, the data structure wouldn't be exactly be a table. I guess there'd be other stuff you can have, assignment operator, and it just directly references that. Cool. Could have used any abstract symbol. Initial is a lexeme that is mapped to the token ID 2, where 2 points to the symbol table for entry for initial. So yeah, initial would map to ID 2, and that would point us to the value in the table. Same with the plus, mapped to the token. Rate is a lexeme that is mapped to the token ID 3, same thing. That's an operator. 60 is a lexeme. Yeah, that's interesting. So how do you handle like literal, like raw literals? That's super interesting because they can look like a bunch of different things. They can be like strings, booleans, floats. Like, yeah, that is interesting. They can even be like, they can even be in C++. They can be binary, like binary. They can look like that sort of thing. Yeah, cool, interesting. But there is a note. Technically speaking, for the lexeme 60, we should make up a token like number 4, where 4 points to the symbol table for the internal representation of integer 60, but we shall defer the discussion of tokens for numbers until chapter 2. Alright, we won't worry about it now. Chapter 3 discusses techniques for building lexical analyzers. Blanks separating the lexemes should be discarded by the lexical analyzer. Figure 1.7 shows a representation of the assignment statement after lexical analysis as the sequence of tokens. Cool, so we've converted it to our literally just a sequence of references to the symbol table. In this representation, the token names equals, plus, and asterisks are abstract symbols for the assignment, addition, and multiplication operators, respectively. Here we go. So we start with our initial string, our initial stream, with lexical analyze it, which maps that to the symbol table. Then we create our abstract syntax tree using our tokens. So it's interesting that this goes into more detail on what a token is, and using tokens this way, that's yeah, it's cool. And then I guess we do. How would you even read that? You'd have to go. You'd have to go from the lowest to the top. You have to start from the bottom and go to the top. So it's like reading it in reverse order. Anyway. So after the semantic analyzer, looks like it adds an extra step in converting 60 into a float. I guess intermediate code generator gives us well, it could give us a control flow graph, but here it's giving us, I guess, this simplified assignment thing. The code optimizer looks like it reduces the amount of commands there into float, is replaced just by literal float string. I guess it gets rid of unnecessary stuff and then gives us our assembly. Wow, okay, so a lot more in depth. This book is great. It's a lot more in depth on the lexical analysis part. So it introduced this symbol table and representing tokens in this way as maps, essentially references to the symbol table. Cool. All right. Okay. I'm not sure there's anything here that I need to remember other than maybe like what is the symbol table? It seems to be like a central, yeah, it's data structure that's central to the entire process almost by the looks of it, because everything references the symbol table from what I can, well, from what it said. It's a data structure that contains the the mappings from the lexical analysis phase. And actually, it will probably contain more now that I look at it. Like when the semantic analyzer does its type checking, it's probably going to be adding stuff to the symbol table. It's probably adding types to the symbol table. But anyway. Cool. Okay, the second phase of the compiler is syntax analysis or parsing. The parser uses the first components of the tokens produced by the lexical analyzer to create a tree-like intermediate representation that depicts a grammatical structure of the token stream. A typical representation is a syntax tree in which each interior node represents an operation and the children of the node represents the arguments of the operation. Yep, we already saw that. This tree shows the order in which operations in the assignment are to be performed. Yep, so this tree shows us this. We already saw that. So yeah, the parent nodes are the the operators, and the child nodes are the tokens, basically. The tree has an interior node labeled asterisk with ID 3 as its left child, and the integer 60 as its right child. The node ID 3 represents the identifier rate. The node labeled asterisk makes it explicit that we must first multiply the value of rate by 60. The node labeled plus indicates that we must add the result of this multiplication to the value of initial. So yeah, it's saying that we have to do this one first. We have to times ID 3 by 60, and then we have to plus the result of that to ID 2, and then we have to assign the result of that to ID 1. Pretty simple. This ordering of operations is consistent with the usual conventions of arithmetic, which tell us that multiplication has higher precedence than addition, and hence that the multiplication is to be performed before the addition. So there's obviously some formula to how that is, to how the laws of arithmetic are applied. I'm guessing, well, I guess the lower they are in the tree, the more precedence they take. So I'm sure we'll learn that. Subsequent phases of the compiler use the grammatical structure to help analyze the source program and generate the target program. Chapter 4, we should use context-free grammars to specify the grammatical structure of programming languages and discuss algorithms for constructing efficient syntax analyzers automatically from certain classes of grammars. We shall see that syntax-directed definitions can help specify the translation of programming language constructs. So what is a context-free grammar? What the heck is that? A set of recursive rules used to generate patterns of strings. Context-free grammars are used to describe context-free languages. It's a set of recursive rules used to generate patterns of string. A context-free grammar can describe all regular languages and more, but they cannot describe all possible languages. Theoretical computer science, compiler design, linguistics. CFG is used to describe programming languages and parser programs and compilers. Two parse trees that describe CFGs that generate the string x plus y times z. Okay. So yeah, if you get rid of these s's, it's essentially what the tree that we were looking at before. Okay, so a context-free grammar is basically this. Yeah, it's basically this, the tree structure we're looking at. Cool, okay. With these s's. Cool. Well, we will get to that in the future, so I'm not going to put that in Anki. In chapters 2 and 5, we shall see that syntax-directed definitions can help specify the translation of programming language constructs. Syntax-directed definitions. Syntax-directed definitions can help specify the translation of programming language constructs. Well, I guess we'll find out in chapters 2 and 5. Semantic Analyzer uses the syntax tree and the information in the symbol table to check the source program for semantic consistency with the language definition. It also gathers, so we already knew what that was, language consistency and language correctness according to the spec or the definition of the language. It also gathers type information and saves it in either the syntax tree or the symbol table. Okay, there you go. So we can save things in the syntax tree. Interesting. For subsequent use during intermediate code generation, an important part of semantic analysis is type checking, where the compiler checks that each operator has matching operands. For example, many programming languages require an array index to be an integer. Fair enough. The compiler must report an error if a floating point number is used to index an array. Fair enough. The language specification may permit some type conversions called coercions. Yep. For example, a binary arithmetic operator may be applied to either a pair of integers or to a pair of floating point numbers. Yep. If an operator is applied to a floating point number and an integer, the compiler may convert or coerce the integer into a floating point number. Cool. Such a coercion appears in figure 1.7. Suppose that position, initial, and rate have been declared to be floating point numbers and that the lexeme 60 by itself forms an integer. The type checker in the semantic analyzer in figure 1.7 discovers that the operator asterisk is applied to a floating point number rate, and the integer 60 in this case converts it using this interfloat. Has an extra node for the operator interfloat, which explicitly converts as integer argument. Yep, so pretty straightforward. Here it tries to add an integer, it tries to add a float to an integer, has to add another step, adds it here, converts the int to a float. Easy stuff. Intermediate code generation. In the process of translating a source program into target code, a compiler may construct one or more intermediate representations, which can have a variety of forms. Syntax trees are a form of intermediate representation. They are commonly used during syntax and semantic analysis. After syntax and semantic analysis of the source program. Many compilers generate an explicit low-level or machine-like intermediate representation, which we can think of as a program for an abstract machine. This intermediate representation should have two important properties. It should be easy to produce and it should be easy to translate into the target machine. In chapter 6, we discovered an intermediate form called 3-address code, which consists of a sequence of assembly-like instructions with 3 operands per instruction. Each operand can act like a register. Okay, yeah, so that's what this code was up in the intermediate code generator. So 3 operands. In this example, we have 1 operand here, operand here, operand here. Here we have, is that 3 operands? I guess that's 3 operands. Only 2 here. Yeah, so I get it. Like it behaves like assembly. Fair enough. So it's easy to translate into assembly and machine code. There are several points worth noting about 3-address instructions. First, each 3-address assignment instruction has at most 1 operator on the right side. Yep. Thus, these instructions fix the order in which operations are to be done. The multiplication precedes the addition in the source program. Second, the compiler must generate a temporary name to hold the value computed by a 3-address instruction. Temporary name to hold the value computed by a 3-address instruction. So yeah, T1, T2, T3, ID1. Third, some 3-address instructions, like the first and last in the sequence above, have fewer than 3 operands. Yes, so this one only has 2, this one only has 2. That's obviously illegal. In chapter 6, we cover the principal intermediate representations used in compilers. So there's obviously a bunch of these, I'm sure. Chapter 5 introduces techniques for syntax-directed translation that are applied in chapter 6 to type checking and intermediate code generation for typical programming language constructs such as expressions, flow of control constructs, and procedure calls. Techniques for syntax-directed translation that are applied in chapter 6 to type checking and intermediate code generation for typical programming. Yeah, I guess it would get pretty can get pretty complex with flow control stuff. Yeah, calling other functions, like all the different parameters, parsing all that would be, or representing all that could get pretty difficult. At least in terms of the 3-address code for sure. So I've been going for an hour. I'm gonna have a quick break. I'm gonna have a 5-minute break. I'll be back. Alright, we're back. So, code optimization. The machine-independent code optimization phase attempts to improve the intermediate code so that better target code will result. Usually better means faster, but other objectives may be desired, such as shorter code or target code that consumes less power. Again, I don't understand that one. It's consuming less power because obviously if your code is shorter, yeah, whatever. For example, a straightforward algorithm generates the intermediate code. 1.3, yep. Using an instruction for each operator in the tree representation that comes from the semantic analyzer. A simple intermediate code generation algorithm followed by code optimization is a reasonable way to generate good target code. The optimizer can deduce that the conversion of 60 from integer to floating point can be done once and for all at compile time. So the int to float operation can be eliminated completely by replacing the integer 60 by the floating point number 60.0. Moreover, T3 is used only once to transmit its value to ID1 so that the optimizer can transform into the shorter sequence. What? T3 is used only once to transmit its value to ID1 so that the optimizer can transform into the shorter sequence. T1 equals ID3 times 60. Yep. ID1 equals ID2 plus T1. Cool. There is a great variation in the amount of code optimization different compilers perform. In those that do the most, the so-called optimizing compilers, a significant amount of time is spent on this phase. There are simple optimizations that significantly improve the running time of the target program without slowing down compilation too much. The chapters from 8 on discuss machine-independent and machine-dependent optimizations in detail. Hell yeah, I love that stuff. So that's going to be super interesting. 1.2.6 Code Generation. The code generator takes as input an intermediate representation of the source program, maps it into the target language. If the target language is machine code, registers or memory allocations are selected for each of the variables used by the program. Then the intermediate instructions are translated into sequences of machine instructions that perform the same task. Intermediate instructions are translated into sequences of machine instructions that perform the same task. A crucial aspect of code generation is the judicious assignment of registers to hold variables. I wonder why it's so crucial. I guess we'll find out. For example, using registers R1 and R2, the intermediate code in 1.4 might get translated into the machine code. Okay, it looks like we're loading this variable into register 2. Looks like we're multiplying by, I don't know what the F means, but we're multiplying 60 by whatever's in the register, and we're storing that in the register. We're loading another variable into register 1. We're adding whatever's in register 2 to whatever's in register 1, and then we're storing that result in register 1. Then we are storing whatever's in register 1 into the variable ID1. I hope I'm right. I hope I'm interpreting that correctly. The first operand for each instruction specifies a destination. The F in each instruction tells us that it deals with floating point numbers. Okay, fair enough. The code in 1.5 loads the contents of address ID3 into register. Yeah, well, yeah, it's literally telling us what it's done. Then it multiplies it with some floating point constant. The pound sign signifies that 60 is to be treated as an immediate constant. The third instruction moves ID2 into register R1, and the fourth adds to the value previously computed in register R2. Yep. Finally, the value is stored in the address. Yeah, cool. I got it right. Hell yeah. So the code correctly implements the assignment statement. Chapter 8 covers code generation. This discussion of code generation has ignored the important issue of storage allocation for the identifiers in the source program. As we shall see in Chapter 7, the organization of storage at runtime depends on the language being compiled. The organization of storage at runtime depends on the language being compiled. Right, because storage allocation decisions are made either during intermediate code generation or during code generation. Okay. Here we go, symbol table management. I want to learn a bit more about this. An essential function of a compiler is to record the variable names used in the source program and collect information about various attributes of each name. These attributes may provide information about the storage allocated for a name. Its type, its scope, where in the program its value may be used, and in the case of procedure names, such things as the number and types of its arguments, the method of passing each argument, for example by value or by reference, and the type returned. Cool, I like it. The symbol table is a data structure containing a record for each variable name with fields for the attributes of the name. The data structure should be designed to allow the compiler to find the record for each name quickly and store or retrieve data from that record quickly. Symbol tables are discussed in Chapter 2. Awesome, I'm looking forward to learning about those. The grouping of phases into passes. The discussion of phases deals with the logical organization of a compiler. In an implementation, activities from several phases may be grouped together into a pass that reads an input file and writes an output file. For example, the front-end phases of lexical analysis, syntax, semantic, and intermediate code generation might be grouped together into one pass. Okay? I guess it's like some sort of industry thing. Code optimization might be an optional pass. Then there could be a back-end pass consisting of code generation for a particular target machine. Some compiler collections have been created around carefully designed intermediate representations that allow the front end for a particular language to interface with the back end for a certain target machine. With these collections, we can produce compilers for different source languages for one target machine by combining different front ends with the back end for that target machine. We can produce compilers for different source languages for one target machine by combining different front ends with the back end. Oh, that's cool. All right. Nice. Similarly, we can produce compilers for different target machines by combining a front end with back ends for different target machines. Yeah, cool. That's awesome. I'm assuming that G++ has what I'm guessing is that G++ is some set of, it's like a library of different front ends and back ends. Let's see if we can get any more info on that. Possibly not from the man page. Yeah, I probably have to go on their website for that. Yeah. Cool. You know what, let's do that. Let's do that. GCC front ends. The main GCC distribution contains the front ends for C, C++, Objective-C. Oh. Oh shit, I did not know that it could it could compile Fortran, Go, D. I did not know that. There are several more front ends for different languages that have been written for GCC but not yet integrated into the main distribution. Cool. Some of these front ends are very much works in progress. Others are very mature. The Pascal compiler, pretty cool. COBOL. Awesome. I wonder if front end, back end. It may not tell us information. Yeah, awesome. Anyway, that's getting off. Yeah, let's get back on track. So, compiler construction tools. The compiler writer, like any software developer, can profitably use modern software development environments containing tools such as language editors, debuggers, blah, 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 blah. In addition to these language, general software development tools, other more specialized tools have been created to help implement various phases of a compiler. These tools use specialized languages for specifying and implementing specific components. Sophisticated algorithms. The most successful tools are those that hide the details of the generation algorithm and produce components that can easily be integrated into the narrative. So this goes back to the declarative style that we're talking about. So more abstraction by the sounds of it. Some commonly used compiler construction tools include parser generators. What's a parser generator? Automatically produce syntax analyzers from a grammatical description of a programming language. How do you... What? How do you give a grammatical description of a programming language in the first place? And then how do you generate a parser from that? That seems wild, but that's really cool. Scanner generators that produce lexical analyzers from a regular expression description of the tokens of a language. Okay. That is also cool. So when you go to do lexical analysis, you can give it a regular expression description of the tokens of a language. That's wild. That's pretty cool. Syntax directed translation engines. They produce collections of routines for walking a parse tree and generating intermediate code. Code generator generators produces a code generated from a collection of rules for translating each operation of the intermediate language into the machine language. Holy shit, this is insane. Data flow analysis engines that facilitate the gathering of information about how values are transmitted from one part of a program to each other part. Data flow analysis is a key part of code optimization. Awesome. Compiler construction toolkits that provide an integrated set of routines for constructing various phases of a compiler. Awesome, awesome, awesome. I'm glad somebody made this stuff so that I don't have to make it myself. We shall describe many of these tools throughout this book. 1.3 The evolution of programming languages. The first electronic computers appeared in the 1940s and were programmed in machine language by sequences of zeros and ones. Very low level. Needless to say, this kind of programming language was slow, tedious. Yep. Moved to higher level languages. First step towards more people-friendly programming languages was the development of mnemonic assembly languages in the early 1950s. Initially, the instructions in an assembly language were just mnemonic representations of machine instructions. Later, macro instructions were added to assembly languages so that a programmer could define parameterized shorthands for frequently used sequences of machine instructions. Good stuff. A major step towards high-level languages was made in the latter half of the 1950s with the development of Fortran for scientific computation, COBOL for business data processing, and Lisp for symbolic computation. I have no idea what symbolic computation is. I'm just quickly going to Google that. Concerned with algorithmic manipulation of symbolic objects. What are symbolic objects? Oh my god. Symbolic computation is concerned with algorithmic manipulation of symbolic objects. These can be objects in formal language such as formulas or programs, or algebraic objects such as polynomials. Okay. Some mathematical related stuff. Alright. Symbolic programs, right. Yeah, because writing formulas and stuff is pretty difficult, and lots of computation around that. These languages are so successful that they're still in use today. In the following decades, many more languages were created with innovative features to help make programming easier, more natural, and more robust. Later in this chapter, we shall discuss some key features that are common to many programming languages. Today, there are thousands of programming languages. They can be classified in a variety of ways. One classification is by generation. First generation, obviously machine languages. Second generation, assembly languages. Third generation, high-level stuff, Fortran, COBOL, Lisp, C, C++, and Java. Fourth generation are languages designed for specific applications like Nomad for report generation, SQL for database queries, and PostScript for text formatting. The term fifth generation language has been applied to logic and constraint-based languages like Prolog and OPS 5. What is Prolog? High-level computer language first devised for artificial intelligence applications. Prolog has been used largely for logic programming, and its applications include natural language understanding and expert systems such as MySyn. I'm not sure what that is. Cool. Okay, so it's like an AI logic language. Awesome. Where are we? Another classification of languages uses the term imperative for languages in which a program specifies how a computation is to be done, and declarative. A program specifies what computation is to be done. Languages such as C, C++, C#, Java are all imperative. Imperative languages, there's a notation of program state and statements that change the state. Functional languages such as ML and Haskell and constraint logic languages such as Prolog are often considered to be declarative languages. The term von Neumann language is applied to programming languages whose computational model is based on the von Neumann computer architecture. Many of today's languages, such as Fortran and C, are von Neumann languages. I've never heard of the von Neumann computer architecture, so let's find out what that is. Von Neumann architecture, also known as the von Neumann model or Princeton architecture, based on a description by John von Neumann. The document describes the design architecture for an electronic digital computer with these components. A processing unit with an ALU and registers, a control unit that uses an instruction register and a program counter, memory. Alright, okay. So basically, yeah, like modern CPUs, basically. Cool. An object-oriented language is one that supports object. Yes, we all know what that is. Scripting languages are interpreted language with high-level operators designed for gluing together computations. These computations were originally called scripts: Awk, JavaScript, Perl, PHP, Python, Ruby. Programs written in scripting language are often much shorter than equivalent programs. Impacts on compilers. Since the design of programming languages and compilers are intimately related, the advances in programming languages place new demands on compiler writers to devise algorithms and representations to translate and support the new language features. Since the 1940s, computer architecture has evolved as well. Not only did compiler writers have to track new language features, they also had to devise translation algorithms that would take maximal advantage of the new hardware capabilities. Yeah, I feel like it would be such a crazy industry to be in, as it's like constantly changing, constantly having to adapt to new architectures and new backends, new front ends, whatever. Compilers can help promote the use of high-level languages by minimizing the execution overhead of the programs written in these languages. Compilers are also critical in making high-performance computer architectures effective on users' applications. Hell yeah, they are. In fact, the performance of a computer system is so dependent on compiler technology that compilers are used as a tool in evaluating architectural concepts before a computer is built. That's interesting. Compiler writing is challenging. A compiler by itself is a large program. Moreover, many modern language processing systems handle several source languages and target machines within the same framework. That is, they serve as collections of compilers. Yeah, as I was saying with G++, possibly consisting of millions of lines of code. Consequently, good software engineering techniques are essential for creating and evolving modern language processors. A compiler must translate correctly the potentially infinite set of programs that could be written in the source language. Yeah, that's what I was thinking about earlier. I was saying I'm not sure how you can have a 100% correct compiler because there is an infinite set of programs that could be written in the source language. The problem of generating the optimal target code. I guess there is still only a finite set of possible lexical patterns that you could have though. That would make sense. There's still only a finite set of possible tokens, token arrangements that you could have, I guess. Maybe. The problem of generating the optimal target code from a source program is undecidable in general. The problem of generating the optimal target code from a source program is undecidable in general. Thus, compiler writers must evaluate trade-offs about what problems to tackle and what heuristics to use to approach the problem of generating efficient code. I'm going to seem really dumb, but what does heuristics mean again? Totally forgot that. Heuristics are mental shortcuts for solving problems in a quick way that delivers a result that is sufficient enough to be useful. Okay. Compiler writers must evaluate trade-offs, what problems to tackle, and what heuristics to use to approach the problem of generating efficient code. A study of compilers is also a study of how theory meets practice, as we shall see in section 1.4. The purpose of this text is to teach the methodology and fundamental ideas used in compiler design. It is not the intention of this text to teach all the algorithms and techniques. Obviously, however, readers of this text will acquire the basic knowledge. Okay, indicate which of the following terms apply to which of the following languages. Imperative applies to C, C++, I can't remember. I've never used COBOL. I've never used Fortran. I don't know much about them. Java is imperative. Lisp, I'm not sure. ML is not imperative. But I know Python is imperative. I don't know. I've never used Perl and Visual Basic. Not sure. Declarative, I know ML is declarative. Anything else there? Declarative. I'm not sure. Leave it in the comments if you know the answer to this. Yeah, I'm just going to do some quick Googling. Is COBOL declarative? Nope, it's imperative. Cool. Von Neumann. So I'm guessing C, C++. I think he said Fortran was von Neumann architecture as well. Like a von Neumann language, that is. I don't remember which other ones these are. I don't remember the rest. Object-oriented. C is not. C++ is. COBOL, Fortran, I don't believe are. Java is. Lisp, I have no idea about. Never used it. ML, no, that's not object-oriented. If it's a functional language. Perl sounds like it would be object-oriented. Python, yes. Visual Basic, I don't know the answer. I never used it. Is Visual Basic It is. Functional. I know ML is functional. Lisp, I don't know. Is Lisp functional? Yep. So Lisp is a functional programming language. There you go. Third generation. Looks like most of them are third generation. I think I'm gonna say all of them are third generation. If I'm wrong, let me know in the comments. Fourth generation. Okay, maybe maybe oh, maybe ML is the exception to that. I don't know. Is ML a fourth generation language? Don't think so. Here we go. Not sure. And scripting languages. So Perl, definitely. Python, definitely. Visual Basic, not sure. Lisp, no, I don't think so. Perl, Python for sure. Okay. Last little section. The science of building a compiler. Compiler design is full of beautiful examples where complicated real-world problems are solved by abstracting the essence of the problem mathematically. They serve as excellent illustrations of how abstractions can be used to solve problems. Take a problem, formulate a mathematical abstraction that captures the key characteristics, and solve it using mathematical techniques. The problem formulation must be grounded in a solid understanding of the characteristics of computer programs, and the solution must be validated and refined empirically. What does it mean to validate something empirically? I'm not sure what that means entirely. Empirical validity, also called statistical or predictive validity, describes how closely scores on a test correspond with behavior as measured in other contexts. Let's get a bit more info on that. Students' scores on a test of academic aptitude, for example, may be compared with their school grades. Oh my god. I'm not going to pay you money. You will not get my money today or ever. Empirical evidence for a proposition is evidence that supports or counters this proposition. That is. Alright, so it just means basically using evidence to validate the computer programs. A compiler must accept all source programs that conform to the specification of the language. The set of source programs is infinite, and any program can be very large, consisting of possibly millions of lines of code. Any transformation performed by the compiler while translating a source program must preserve the meaning of the program being compiled. Compiler writers thus have an influence over not just the compilers they create, but all the programs that their compilers compile. I did not think of that. That's pretty big implication. This leverage makes writing compiler is particularly rewarding. However, it also makes compiler development challenging. Modeling. The study of compilers is mainly a study of how we design the right mathematical models and choose the right algorithms while balancing the need for generality and power against simplicity and efficiency. Some of the most fundamental models are finite state machines and regular expressions. Cool. Yeah, I want to learn about more about finite state machines for sure. And regular expressions, which we shall meet in Chapter 3. These models are useful for describing the lexical units of programs, keywords, identifiers, and such, and for describing the algorithms used by a compiler to recognize those units. Also among the most fundamental models are context-free grammars. Here it is again, used to describe the syntactic structure of programming languages such as the nesting of parentheses or control constructs. Yeah, okay, cool. So, we'll be using finite state machines, regular expressions, context-free grammars, abstract syntax trees, control flow diagrams, all these different models to help us build these compilers. We shall study grammars in Chapter 4. Similarly, trees are an important model for representing the structure of programs and their translation into object code. Optimization. The term optimization in compiler design refers to the attempts that a compiler makes to produce code that is more efficient than the obvious code. Optimization is thus a misnomer, since there is no way that code produced by a compiler can be guaranteed to be as fast or faster than any other code that performs the same task. In modern times, the optimization of code that a compiler performs has become both more important and more complex. It's more complex because processor architectures have become more complex, yielding more opportunities to improve the way code executes. It is more important because massively parallel computers require substantial optimization or their performance suffers by orders of magnitude. Interesting. With the likely prevalence of multi-core machines, computers with chips that have very large numbers of processors on them, all compilers will have to face the problem of taking advantage of multiprocessor machines. It is hard, if not impossible, to build a robust compiler out of hacks. Thus, an extensive and useful theory has been built up around the problem of optimizing code. That's interesting. So, I want to learn more about that. The use of a rigorous mathematical foundation allows us to show that an optimization is correct and that it produces the desirable effect for all possible inputs. I love to hear that. That's cool. We shall see, starting in Chapter 9, how models such as graphs, matrices, and linear programs are necessary if the compiler is to produce well-optimized code. On the other hand, pure theory alone is insufficient. Like many real-world problems, there are no perfect answers. In fact, most of the questions that we ask in compiler optimization are undecidable. One of the most important skills in compiler design is the ability to formulate the right problem to solve. We need a good understanding of the behavior of programs to start with, and thorough experimentation and evaluation to validate our intuitions. Compiler optimizations must meet the following design objectives. 1. The optimizations must be correct, that is, preserve the meaning of the compiled program. The optimization must improve the performance of many programs. The optimization time must be kept reasonable, and the engineering effort required must be manageable. It's impossible to overemphasize the importance of correctness. It is trivial to write a compiler that generates fast code if the generated code need not be correct. Optimizing compilers are so difficult to get right that we dare say that no optimizing compiler is completely error-free. Thus, the most important objective in writing a compiler is that it is correct. On that topic, if you look at the front page of the CS4120, you'll see this link here, results from the 2023 compiler bake-off, which I'm guessing are the students' attempts at building compilers, and then they benchmark it and test against each other. You can see down here we have on the x-axis we have the speed. Looks like it's well below 1 millisecond. And then, yeah, obviously, and then the code, the compiler correctness on the y-axis. So you can see like this group here got a correctness of 94%, but this group here was faster. Obviously, they got less correctness. So which one is better? I guess the one with the most correctness, but then the one with the most correctness is over here, and it's significantly slower than the 94%. So yeah, so it's interesting to see that, like, you're not gonna get. I'm just not sure like 100% is even possible, but I guess the book said it is, so we'll see it in effect. Bro, these guys were so fast with only 4% correctness. Good try. The second goal is that the compiler must be effective in improving the performance of many input programs. Normally, performance means the speed of the program execution, especially in embedded applications. We may also wish to minimize the size of the generated code. Fair enough. And in the case of mobile devices, it is also desirable that the code minimizes power consumption. Okay. Typically, the same optimizations that speed up execution time also conserve power. Oh, there you go. Okay, yeah. That's what I assumed. Consuming power is literally just speeding up execution and reducing, like, clock cycles or operations, I guess. Besides performance, usability aspects such as error reporting and debugging are also important. Third, we need to keep the compilation time short to support a rapid development and debugging cycle. This requirement has become easier to meet as machines get faster. Often a program is first developed and debugged without program optimizations. Not only is the compilation time reduced, but more importantly, unoptimized programs are easy to debug because the optimizations introduced by a compiler often obscure the relationship between the source code and the object code. And on a side note, I guess the optimizations themselves have to be tested rigorously as well. Turning on optimizations in the compiler sometimes exposes new problems in the source program. Thus, testing must again be performed on the optimized code. The need for additional testing sometimes deters the use of optimizations in applications, especially if their performance is not critical. Finally, a compiler is a complex system. We must keep the system simple to assure that the engineering and maintenance costs of the compiler are manageable. There are an infinite number of program optimizations that we could implement, and it takes a non-trivial amount of effort to create a correct and effective optimization. We must prioritize the optimizations, implementing only those that lead to the greatest benefits on source programs encountered in practice. Makes sense? Thus, in studying compilers, we learn not only how to build a compiler, but also the general methodology of solving complex and open-ended problems. I love that. That's what we're here for. We're here to destroy complex problems. Let's go. The approach used in compiler development involves both theory and experimentation. We normally start by formulating the problem based on our intuitions on what the important issues are. Okay, that wraps up the reading for lesson 1. This book is excellent. I see why this book is like legendary. We're going to do it. We are going to destroy this beast of, we're going to destroy the dragon that is the complexity of compiler design. Yeah, cool. All right. That was a good session. Next session, we'll be moving on to lesson 2, which is lexical analysis and learning about regular expressions. Something that I know very little about, regular expressions. So that'll be fun. Thank you for watching. I'll see you next time.